We will now start the first session, and we will hear two talks. We have Norman Huck and Carola Hein, and we will start with Norman. And I'm very glad that you are here, Norman. Welcome. And Norman Huck is an architect and researcher in the field of digital building fabrication, and he studied in Wismar, in Vienna at the University of Technology, at the Architectural Association, where he did his master in emergent technologies and design. And after graduating, he went to the architecture office Herzog de Meuron to work as a programming architect, which is probably not about room program, but more about coding, because it was in the digital technologies group at HDM. And this deepened research or interest in digital design led him go back into research. He started a PhD position at Gramazio Kohler Research at the ETH in Zurich, where he received his doctorate in 2018. And currently, Norman Huck is Junior Professor for Digital Building Fabrication at the Institute for Structural Design at the TU Braunschweig. In Norman's research, he's challenging conventional ways of processing concrete, and he investigates reinforcement strategies for 3D printed concrete, a topic which is not often covered when it comes to 3D printing. But I kind of like the story, how this research unfolded from something that in the beginning went into a slightly different direction. But let Norman tell this story. Very welcome. Thank you for being here, and the floor is yours.
Thank you, Oliver, for the introduction. I'll just start sharing my screen and set up everything. So we do it like this. Hold on. I need to optimize it. Share. All right. I can't see you anymore, but I hope you can see my screen. Is that correct? Can I?
Yes, we see your screen.
Yeah. Okay. Perfect. Yeah. Thank you again, Oliver, for the introduction and the spontaneous possibility to stand in for another speaker. I already had the pleasure to present at the first BEAM Symposium. I think it was in 2016. Where I presented my, at that time, ongoing research of Gramazio Kohler. And last year, the head of our institute, Harald Kloft from TU Braunschweig, presented our current work on shotcrete 3D printing. So for today, what I want to do is to present as well our current investigations into reinforcement strategies for additive manufacturing. And I want to kind of bridge this time from the first presentation and until now, and present today how this related or how this work is a kind of continuous or shows a continuous thread. So recently we have published a classification approach on reinforcement strategies for additive manufacturing, which is kind of broadly divided into three categories. Firstly, we have a category of reinforcement techniques where the concrete supports the reinforcement during the process of printing. For example, there's a core is being printed, and then rods are being placed, or carbon tapes are laid, nails are shooted, or for example, fibers are dispersed into the concrete stream. So this is a category of processes where the concrete really helps the reinforcement to stay in the correct position, and where no additional support material is needed, as for example in conventional reinforcement cages. And secondly, we investigate a category which is basically the inverse of it, where the reinforcement supports the concrete, kind of as an additional formwork or as kind of a stay-in-place formwork, which gives additional freedom to the geometries which can be printed, for example, overhangs. And thirdly, and this is something I think that blends in nicely with some of the talks that we've heard today, but which I'm not going to cover in detail, is an incremental process, or our incremental processes where the concrete deposition and the placement of reinforcement by, for example, one welding happen simultaneously. But I'm not going to talk so much about the third version, but today rather focus on two of these classifications, or these two strategies. The first being reinforcement supports concrete. That is a strategy that I followed in the mesh mold research at ETH Zurich. And the second, the inverse of it, is basically concrete supports reinforcement, where there is first a concreting process and then a reinforcement process. So let's start with mesh mold and give a bit of history of this project. The inspiration to this project was really threefold. Firstly, that concrete structures, or that the cost of formwork for concrete structures really makes a significant amount of the cost share of the total costs. That is about 50% for simple geometries, and it increases exponentially with geometric complexity and can make up to almost 90% of the entire costs. Second aspect is the high amounts of waste that is created when fabricating one-of-a-kind formwork, and this is an example from the EPFL Learning Center in Lausanne. So each concrete formwork piece is one of a kind and then often discarded after concreting. And thirdly, and this is I think still one of the large challenges in 3D printing with concrete, is the integration of reinforcement into the printing process. So mesh mold there went another way. The idea was that a robot fabricates a dense mesh directly on the construction site, which acts as formwork to support the concrete while it's still wet, and which remains within the concrete after the concrete has cured, and then acts as structural reinforcement. And this research started very conceptually with this spatial 3D printing process, where material is extruded in mid-air and then is cooled down so that it solidifies and stiffens, so that we can print these filigree meshes that can be adjusted towards the specific needs. So it can have different curvature radii, different mesh sizes, different thicknesses, all according, for example, to the loads that act on the respective building element. And this was tested in the small scale. It showed very nicely that the high amount of spatial connections really stiffens the structure. So this mesh weighs in total only 120 grams, but supports over 60 kilogram of wet concrete without deformation. And of course, this process also offers the possibility to differentiate the meshes according to the performative requirements that act on these. For example, on the left side, you see the undifferentiated triangulated mesh, but you can also make it less dense in the middle, or deepen the perimeter to make it more stiffer, or introduce these vertical channels so that concrete can be filled into the structure. And of course, also on the concrete side, there are certain requirements to the thixotropic behavior of the material. As shown here, the material rests basically within the mesh, and then as soon as kinetic energy is introduced by this vibrating device, the material sinks into the shape and rests inside the formwork. So this turned out quite nicely regarding the formwork aspect, but of course in structural demands, the ABS, the material that we used here, didn't really comply with the structural necessities of the system, so that in a second experimental phase, we opened up the research to a broader range of disciplines, and we collaborated with roboticists, with structural engineers, with material scientists, and partners from industry to translate the system from plastic into steel. And other than the WAM examples that we saw today already, here we used semi-finished steel wires, so basically conventional off-the-shelf steel elements, which of course kind of limits the geometric freedom of those meshes, but at the same time it increases the speed of fabrication. So these were really the first examples. What's compelling here is also that in usual industrial processes, you often have the machines being multiple times bigger than the object that they are producing. And here this principle is kind of inverted. So you have this miniature factory that's basically hovering over the structure to fabricate meshes. And once these meshes are fabricated, then the concreting process becomes quite easy. It doesn't require precision anymore. It's basically just dumping the concrete or pumping it into the mesh, and it automatically takes the right shape. Of course, the surface finishing is then another aspect of it. So here, this was done manually in a craft-based process, but we will hear more about automating this process later. So the example that I've shown you just now was based on 2 millimeter steel wires, which still doesn't comply with any building codes. So here we evolved this tool head, incorporated more powerful components, and so that we became able to process steel rebars up to 8 millimeter of diameter. So these were then also tested. Basically, also the concreting process was being scaled, and here we worked with the material scientists together to develop a concrete that is basically let's say an impossible mix, because on one hand it should avoid that voids are created within the structure, so it should be very fluid, and the other hand, it should not like run out of the mesh to create material losses. So what the scientists came up with was a mix that's called spaghetti and meatballs. So basically it has large aggregates, recycled aggregates that make the structure denser, and then fibers that are clogging the mesh openings. And then again, we had this surface finishing part using shotcrete, and produced the first demonstrators, which were part of a larger structure. And this larger structure was then going to be erected at the DFAB house in Zurich. And the DFAB house is a large-scale demonstrator for digital building technologies, and it consists of a whole variety of processes, starting with a robotically assembled timber structure that contains 2 stories. Then the smart slab, where the formwork is printed in a particle bed printing process. Then the smart dynamic casting facade mullions, that are extruded, and then of course also the mesh mold wall, which carries the entire load of the structure above, which is about 80 tons. And the backbone itself doesn't take any load, so it's really the wall is designed for the entire loads of the structure. And it was fabricated using the in situ fabricator. And I will just let this video run. I hope it runs smoothly, which shows the entire process. I don't know if you hear music. Yeah, okay, perfect. Yeah, so this is the tool head with the electrodes. It's based on a resistant wire, it's a resistant welding process. Then the digital workflow, and then the construction on site, where the robot uses these April tags to register its position. So the process based on welding, cutting, and bending. Yeah, so now comes the concreting part, which is still manual, labor intensive, and the concrete is just pumped inside the mesh. This is manual, but could as well be performed robotically. The advantage is that it's quite quick, so it's done within a working day. And the material is sprayed to cover the steel. And here again, the manual surface finishing process. So then the entire structure was 3D scanned, and based on the 3D scan, the ceiling of the next group of the smart slab was generated, so that really a tight fit between these two structural elements could be generated. And these are some interior pictures, and that is the entire building as it was finished last year. Okay, so now I want to report a little bit on the inverse of this structure. So where the concrete actually supports the reinforcement. And this is work that we have been doing in the past 2 years at the Institute of Structural Design at TU Braunschweig, where we have the Digital Building Fabrication Laboratory. It's a kind of large-scale robotic fabrication facility, which contains 2 portals. One that is very suitable for subtractive methods, like you can see here. It's this giant saw blade that can cut, but that can be also employed with milling bits and drills and so on. And then a high payload robot, which is very suitable for additive or formative processes. So one of the processes, or one of the first processes that we have been investigating is the shotcreting process, and this is a process that is very well established. It's about 100 years old. The advantages are that it can be sprayed around reinforcement, that it sticks very well to vertical surfaces, and that the high velocity of the projection compacts the material very well. On the downside is, of course, and this is something that you see in the video, that shotcreting is generally kind of it's like a rather dirty process, often comes with high material losses, and is rather imprecise and very labor intensive. But in combination with robotics and with sensor control, the disadvantages can mostly be eliminated, and the potentials of this fabrication process can be multiplied. So much for the technology. In a recent demonstrator, we then developed a reinforcement strategy, which is based on this concrete supports reinforcement approach, and which is basically the inverse of what I've shown before. So the process starts with an input geometry, some kind of arbitrary double curved wall element, which is then in a computational process modified to include these undulations, so that every 40 centimeters a pre-bent horizontal reinforcement element can be placed, which over the entire height of the structure then creates these kind of vertical channels, where then unbent reinforcement, and in this case we use 12 millimeter rods, can simply be inserted and in a additional vertical printing process can then be embedded structurally, and also automated automated surface finishing with using different troweling devices. So here are some pictures from the process. The robot prints in 3-axis manner. Then these prefabricated rods are laid only on the tips of these undulations. Then we cut the corners to be more precise. Just slide in the reinforcement from above, which is over the entire height, still very flexible, so it doesn't require any pre-bending. And then comes the covering process, where the reinforcement is then embedded and then troweled and surface finished with the other 3X portal. And also here, I would like to show you a video of the entire process. All right, so this is already also the end of my presentation, and I want to make some advertisement on our own behalf and also for those who are interested in the research. As the ETH, we are part of the Transradio, it's a DFG-funded collaborative research center on additive manufacturing in construction, which we are running together with TU München. and where we investigate several additive manufacturing processes on the scale of construction, as well as develop materials and processes, and design and construction procedures. So we have a website which is depicted on the lower right corner, and if you're interested, you're invited to visit this website and contact us if you are interested in collaborations also. And with that, I thank you for your attention, and I'm also welcoming questions from your side. Thank you. Thanks.
Thank you very much, Norman, for this impressive talk. It's always great to see the scale in which you operate in Zurich, but also now in Braunschweig. And I guess that's an important thing to really go one-to-one. What are your thoughts on that? You started small scale. We saw that in the first experiments with the plastic extrusion. Now it's real architectural scale. What does it take to go from model into one-to-one?
Yeah, I mean, many of these things are, you can really test it only on one-to-one scale, but of course, this is also always a tremendous effort that you have to take in terms of materials and labor that is involved in these large-scale experiments. So many of the things that we are testing, we are actually kind of glad to test it at small scale first, and as much as it's possible. So of course, certain things do not scale very well. Others do. For example, we can investigate how reinforcement can be placed in a manual process or pick and place process and so on. So whatever is possible for the sake of being able to work with lean teams, we try to do on the smaller scale, and then eventually test it up to actually verify that these assumptions are correct. Yeah, so for example, we are actually scaling down again. The shotcrete process, as I mentioned, mostly takes 7 to 8 people to operate an experiment, and we're now looking into how can we make it as small as possible so that we can have valid or verify research assumptions also on the smaller scale.
Mm. Thank you. We have questions in the chat. Philip.
Yes, I have 2 questions to add. The first one is, what kind of tools are used for smoothing and cutting?
Yeah, so different ones basically. So for smoothing, we used off-the-shelf products from Rocamaat. It's a firm that builds these handheld devices for cement plaster, and these are basically simple. There's a range of products from plastic discs to steel discs, or these, I don't even know the English name for it, these rotating blades, Flügelglätter in German, that I usually use to smoothen floors. And then for the milling part, we looked for, there are not so many devices that are actually used for cutting wet or like green state concrete, and that we just looked into milling bits, flank milling bits that are usually used for other purposes. But now we are developing our own tools to be more precise or to meet more precisely the requirements of the processes.
Okay, thank you. And then the other question was, what kind of sensors are used for the distance measurements, or what is done with a visible laser?
Yeah, exactly. So it's a simple laser measure. It's a line laser scanner, and it it measures basically just the distance from the nozzle to the deposited material down below to the layer, and we use it in a feedback loop. So if the distance changes, so if the distance becomes too big, we slow down the robot so that more material is deposited. And if the distance becomes too small, we speed up the robot so that less material is deposited. And this way, in this way, we simply try to keep the distance, the pre-calculated distance from the robot nozzle to the deposited material always constant, because then we know that we are at the exact height. And this can be very conveniently be adapted by or adjusted by the robot speed.
All right, thank you. These were the questions to Norman from the chat.
Thank you, Philip. You intentionally excluded the WAM aspect in your talk. However, maybe Gijs, do you have any thoughts on how that could be combined from your point of view?
Yeah, I was glad to see the project proposal a couple months ago. Maybe it was out there longer, but it looked really nice. I think we never really dove into it because we always feared that the printing of the lines is a bit too slow. I wonder what your take on that is. So we print in a good day, we can print something like 2 meters, maybe 2.5 meters per hour of line, and yeah, I would say that slows down the concrete deposition quite a bit.
Yeah, that's actually the main issue with it. I think these two processes operate on different speeds. One possible way or an approach that I've seen lately in a publication from, I don't want to say anything wrong yet. I don't know actually who published it, but it was kind of an abstraction of the one welding process where it's more kind of a stud welding process. So where you take discrete elements and weld them together so that you can create height at higher speeds, which could be a valid solution to increase the building rate of the steel.
Yeah. So if you see the ETH project where you put down a rebar like this and you put another robot that puts down the dot, I would say you can win. Maybe you put down another 30 centimeters each time. With in a like a 20-second motion. So that sounds like the speed that you need. So I'm curious. I mean, also, you know, I do see the benefit of a fully printed rebar because then you can go all organic, and that would be really nice to see. Maybe even, you know, you can print the concrete outer shell, so that you can also keep the concrete in a very organic shape. But yeah, it does feel that it has a chance to remain academic, and if you make it more like a sort of a shared shared manufacturing method with existing rods, then I think it has more chance.
Thank you very much. I'm afraid we have to move on. We are slightly behind. However, it's nice to see how the different project ideas come together today. And I also see many connections. I have tons of questions, but maybe we can discuss more at the end of the day. Thank you again, Norman, for presenting your work.